In this unit, we're going to be building on what we learned in the previous unit with our BJT basics and DC analysis of our BJT. And so we're going to be looking at how we can now take that bipolar junction transistor and use it in circuits to create linear amplifiers. And so this is a topic we sort of briefly mentioned and talked about in the previous unit. And so for more details on that, you can look at page 3-18 and 3-19. But of course, here in this unit, we're going to be diving into a lot more detail. Before we get into all of that detail though, I want to go over just a few important things that we want to keep in mind. So the first is something that we've mentioned before, but again, just to sort of make sure everybody's on the same page here, is that our BJT must be in the forward active mode if we want linear amplification. So must be in our forward active mode, and so remember I'm often just going to abbreviate that FAM. So we have to be in that forward active mode for linear amplification. And so as we sort of talked about at the end of our last unit, this is why it's so important to use our DC biasing to appropriately set our cue point. So importance of DC biasing to set our cue point or our quiescent point or our operating point. So a lot of different names here. And so what we're going to see as we look through some examples once we get to that point is that in this unit we're going to have to do our DC analysis to set our cue point or determine the cue point. Once we've done that, we can then proceed to doing our AC analysis. So the DC analysis is still going to be an important factor. So we want this linear amplification. So sort of a note on that then is if we do have a linear amplifier, what we're going to be doing is sort of using superposition to allow us to separate our DC and AC analysis. So anytime we have linear signals, we can use superposition. And so what this means is that we can sort of quote unquote separate our DC analysis. And so as I was just saying, we're going to initially have to do DC analysis to determine our cue point, and then we can proceed to our AC analysis. And so we're going to say that these DC signals are going to be large signal analysis, and for our AC signals, so we're separating DC analysis and AC analysis. And so our AC analysis, as we're going to see in the following couple of videos, we're going to call these our small signals, where we're going to do our small signal analysis for our AC signals. And again, we'll come back and we'll clarify all that a little bit later. But the main takeaway here is because we are looking at linear amplifiers, we're using this superposition principle to separate our DC and our AC analysis. Okay, one other important thing to note is that we're going to be considering steady state sinusoidal AC analysis. So we'll be considering steady state sinusoidal analysis. Okay, and so a couple of things to note about this. So of course, as you've seen with other circuits, for instance, simple RL, simple RC, or even RLC circuits, there's a lot of interesting stuff that can go on in the transient response of a circuit, but in this case, we're just going to be interested in the steady state. Transient response is either going to be beyond the scope or not relevant depending on what circuit we're looking at. And now to make a point about our sinusoidal analysis, of course we know a lot of signals we deal with in electrical engineering are sinusoidal, but you might be saying, well, why are we going to focus on sinusoidal? What if we have a square wave, for instance, or a triangle wave? And so the answer to that is you can recall that any time varying signal can be represented by a sum of sinusoidal signals using a Fourier series. So Fourier series, there we go. And so basically that kind of drives home the importance of looking at this sinusoidal analysis is because we can make any signal into a sum of sinusoids. So this sinusoidal analysis is going to be relevant to any situation. So one last thing to sort of remind ourselves about before we get into sort of the meat of this BJT amplifier unit is some of the notation that I talked about way back at the start of the class. And the reason this is important is because, again, we're going to be having DC and AC signals in the same circuit. Sometimes we're going to be talking about both of them together. And so we want to make sure we're clear about whether a value is AC, DC, or both. And so if we have, recall if we have a lowercase parameter with an uppercase subscript, so we see examples of that for our IB as well as for our VBE here, then that represents our total instantaneous value. So that would be the combination of AC and DC. If we just have a capital parameter with a capital subscript, then that's going to be our DC value. If we have both lowercase, so a lowercase parameter and a lowercase subscript, then that's going to be AC value. And then finally, if we have an uppercase parameter with a lowercase subscript, that's going to be our phasor value. And so what we're going to see later on when we're dealing with our AC or our small signals, a lot of times we'll kind of use these two notations interchangeably, or maybe we'll, say you have a choice to use these two. But again, just keep this in mind and reference that in the notes as you're looking through some of the later examples or working through the homework.